Okay, so let's see where we are. Yeah, so we are here. Yeah. So yeah, I stated a theorem about the main theorem, and yeah, the next thing would be I guess I could say a few words about.
Oh no, you started with B symmetry.
Yeah, I explained this B symmetry that it's just a compatibility with some sort of Cartan decomposition. So that is sort of the meaning of that B symmetry. And I could say a few words about the Galois theory. So, in order to consider linear equations, one needs lift of Frobenius. And I'm going to consider, for simplicity, the main results are about this case anyway. This lift of Frobenius, the most trivial one. So, G here is GLN. And so the p derivative that applied to the variable is 0. And we want to look at linear equations. Linear differential equations would be simply equations of the form delta u equals alpha times u to the p. And alpha is, I'm assuming that alpha is a matrix, and it's in GLN of, where here, like in Picard-Vessier theory, one needs to fix a ground field. So I want to fix a ground ring. So O is the name for this ground ring. It's inside R. So, and it's, I don't assume anything about it for now, just a ring, a subring, that I'm going to fix. But of course, I want it to be invariant under the p derivation. So, p derivation of anything inside it is inside it. And now I want to define the Galois, a Galois group. I'm going to fix a solution. So U is a fixed solution. And we're trying hard to define the Galois group attached to this solution and over this ring. So in Galois, in Picard-Vessier theory, if you take a solution, which means a system, fundamental system of solutions, you always get the same group. Here, I couldn't prove that. So there are many things that I cannot prove here, but I can prove some things. And that's all I want to tell you. I cannot tell you about what I cannot prove. I can tell you, as one of my friends used to say, we prove what we can, not what we want. So, okay. So I want to attach a group. And the group is as follows. So what you can do is consider the ring generated by the entries of the solution, exactly as in Picard-Vessier theory. And so ring generated by the entries of the solution. And here is what you take. You take all these matrices in n by n with entries in O, with a property that there is an automorphism of O of U of U, ring, an O algebra homomorphism that commutes with delta. This delta, of course, sends this into itself because of this equation. Did I say that alpha? Yeah, I said alpha is with entries here, so delta sends that ring into itself. You want it to commute with delta, and well, most importantly, of course, it should act on U by C. So sigma of U is UC or CU? I think UC. It's only one way it works, not the other way.
Do you really mean to take matrices in the Lie algebra rather than?
That's what I meant.
Oh, okay.
Yeah, that's correct.
It's a Lie algebra. It's German GLN.
Yeah, GLN. Yeah, so these are n by n matrices.
Yeah.
Yeah. I think it's UC like this. Okay. So this is a group for obvious reasons. And the problem is to compute it. So, and I'm going to state a theorem that tells you what this looks like. And so it's kind of similar to what you see in Picard-Vessiot theory, but there are differences too.
What about no new constants condition? In O of U?
This is sort of guaranteed by the fact that this has the least. U is already with entrances in R. Maybe I didn't write this. U is in G, L, and R.
Oh.
And R itself has the least amount of constants to begin with. So, yeah, so R, the only constants in R are the roots of unity and zero,
Yeah.
so you cannot expect less constants.
Right.
So the guy is really small to begin with, but it's also big. So it's big in many senses, but it's small constant-wise.
But you don't care that the constants are in O? They don't have to be.
I don't.
You don't care.
I don't care. Yeah. So this is a tentative definition because it's not clear at all if for other lifts of Frobenius this is what you need to do. And actually, for other lifts of Frobenius, so in more general situations, not this one, but more general, you don't have a Galois group, but you have a Galois set with some funny extra composition, with some funny extra algebraic structure, which is not a group. But I've never been able to come up with the axioms of what that thing is, except in this case where everything is sort of solid, rock solid. Okay, so that looks a little bit like Picard-Vessiot theory. Let's see what it gives. It gives something interesting. So I'll state a theorem. Maybe I should erase this thing.
So last small question, I'm sorry.
Yeah.
When you compose two different sigmas, the corresponding Cs are being added under that plus sub delta, right?
Here you mean?
Yeah.
Yeah.
Okay.
So right. So if you have several sigmas, this is going to correspond to products of C's. Yeah. So you have a ring homomorphism from a ring isomorphism from the sigmas that have this property to the C's that have this property. I just stated it like this to make it clear that this is a subgroup of this is GLN, sorry. Yeah, sorry about this. This is GLN, yeah. This is a subgroup of GLN. Yeah. Maybe this was one of the confusion. Okay. So this looks a little bit like a Picard-Vessiot thing. Let's see what one can prove about these things. So I have a theorem that says that generically So it's gonna say that generically three things happen. But in each, so the theorem is actually three theorems. Each of the theorems says that generically something happens. But in each of the three theorems, the word generically is used in a different sense. And I'll make exactly sure what I mean by genericity. And it's interesting that one theorem says that generically the group cannot be too big. Others say that generically the group cannot be too small. So you will see. Okay, so bear with me for a while. Yeah, so I'm going to state a theorem. Okay, so the first, actually, let's state three theorems. Theorem 1 says this. There exists, and I have to read because the order of the quantifiers is not the same. It's important, of course. It's not the same in the three theorems. And you will see the three genericity things that I'm talking about. So first of all, there is a Zariski closed set, omega. I apologize for sort of reading. You take the fraction field of R, and you take the algebraic closure, but that's not so important. That does not contain 1, such that for any u in the complement, GLN of R minus omega, so you see it's not so important that I take the algebraic closure. You can just take that thing. The following holds. If you write alpha what alpha should be in terms of u, so u is the solution, so alpha would be the coefficients, and if O is a delta subring such that alpha is with coefficients in O. Okay, then this is what happens. G U over O, this Galois group, contains a normal subgroup of finite index, contains a normal subgroup of finite index, normal subgroup of finite index, which is diagonalizable. But over the algebraic closure. So let's try to understand this. So this says that for a generic choice of the solution, the solution is taken generically. If you fix any coefficient ring for the coefficients of the equation, this is very close, up to finite index, is diagonalizable. This is like the normalizer of the torus, of the maximal torus, is like that. It has a finite index subgroup, which is diagonalizable. So this is close to, so morally, this is close, sufficiently small. So sufficiently close to something inside the normalizer of the central of the maximal torus, which is, of course, remember, it's GLN of F1 bar, sort of. Yeah. So it says that the Galois group is almost inside, but not quite, almost inside GLN of F1 bar. So morally it says that the Galois theory, at least generically, has Galois groups inside GLN of F1 bar. This is something that you expect.
Yeah, like the constants.
Yeah, the constants. Yeah. So these are like the constants. It's sort of okay. But it's not true. This is a remark, and there are very funny examples going on. It's not true that this is always a subgroup of this. For non-generic use, that's not true. So there exist use such that I can give examples if I remember them, for which this is not inside M. So it's not true. There's no general theorem that says that the Galois group is in GLN of the constants. Only generically and only up to a finite index. Okay, so what is the proof of this? This is not an easy proof. It uses a result on algebraic groups that I couldn't find anywhere. But it's a result by algebraic groups over the complex numbers. So it's a very, it looks like an exercise for kids who take a course in algebraic groups. But it's not an easy exercise. So if you see, I'm gonna state a lemma, if you see a proof immediately, tell me, please. Okay. I don't think it's such an easy thing, but who knows? I'm going to tell you a lemma. Yeah. The lemma is this. So this is based on the following lemma. Let X inside GLN-C, it doesn't have to be C, you know, it has to be an algebraically closed field of characteristic 0. The lemma, it doesn't have anything to do with complex numbers. Let X be the set of all matrices V in here, in GLN-C, such that two things are true. First of all, if you take, let's see what I wrote here. If you take any power and you do this P thing, so these are powers, usual powers of matrices, and this is raising to the power P every component of the matrix.
Oh, okay.
So they are different things, you see. That's the same thing as V to the P, so these things commute for all M. They don't commute in general, you know. But let's take those that do. And you need one more. This is...
what is M now?
For all integers.
Oh, for all? Wow.
Yeah, for all integers.
Very strong condition.
Yeah, very strong. Yeah. And the conclusion will be strong because you have a strong hypothesis, and the weak conclusion you better forget about. Yeah. Okay. This is strong. Yeah. And the other one is sort of variation of this, but I really need it. V to the M to the P times, I guess, V to the minus M to the P is 1 for all M. Okay. Then X has exactly one component, irreducible component through the origin. So then X has exactly one, a unique component, irreducible component through the origin. And that's the maximal torus. And that is what I called T, the diagonal matrices. Okay, that's I swear it's an exercise for a class in algebraic groups. But it's not trivial, in my opinion. So it took me a while. you just have to consider centralizers of tori, and at some point there is countably many things, and something stabilizes because of something, and so it's one-page proof. Not a big deal. It's an exercise, but it's fun. And there is something fun to it too.
It's so unbelievable.
What?
It's so amazing. It's so different that everything reduces down to the maximal torus.
Yes, yes. Because these are so strong, you know.
Oh, yeah.
Yeah, this is very strong.
Yeah.
As Bill noticed, yeah, these are the strong conditions. But there is something fun about this that shows that it's not completely trivial. If you are a student in algebraic geometry, the first thing that you try to do is look at the Zariski tangent, schematic Zariski tangent space.
Yeah.
So you can take these conditions and look at the schematic Zariski tangent space. So it can take the scheme defined by this, not a variety.
Right.
This is a set. The set. You can take the scheme and take the tangent space of the scheme, and that means simply you take V equals 1 plus epsilon times a matrix, and see what happens. It's the whole space.
Wow.
So the scheme is very non-reduced.
Yeah.
So if you take the scheme given by these equations, the Zariski tangent space of that scheme is the whole GLN, the whole Lie algebra of this. So for some reason, that scheme is very non-reduced, and its reduction, the reduced scheme, has only one irreducible component through the origin.
It shrinks.
Yeah, it shrinks to the, it's a weird thing. But this is an indication that if you, the first temptation that to prove this won't take you anywhere. So the first temptation would be to analyze things infinitesimally. If you try infinitesimally, you get that the thing is the whole space. So there is something going on here. It's not completely trivial. Yeah. So that's what's used. Because once you have a lemma like this, that explains this Galois group being small.
Yeah.
And these conditions really have to do with this very much, because U has this property.
Can you say quickly why N is GLN of the algebraic closure of the field?
Say it again. Why people say this?
Why is it? Yes. Why do they say it?
No. Why? So the
Why
question is, it's not true because there is no truth in mathematics. Just it's not true because this was not defined.
Yeah. Right.
So why do people like to say that this would be the question? Why are people fond of saying that this is that?
Yes, what about N makes it look to them like the right-hand side?
Yes, what, yeah. Okay, why? That's a good question. So the whole story, as I said, begins with Tits claiming that the Weil group of the permutation matrices should be viewed as the GLN of F1.
Okay. I get it.
And so F1 bar, you add some roots of unity.
Yes, I forgot.
Yeah. So that's probably the best.
Okay.
And this is just a sort of a poetic statement, of course.
Yeah.
And this is an equally poetic statement.
Oh, I have a question about the previous. So
is
alpha arbitrary? Or is it chosen so that U exists in R with entries in R or not?
So, so the setting is you take a U, you define alpha by this.
Okay. So
let's do it like that. Yeah. So you start with a U, you define alpha like this by, it's this times the inverse of that, and you take a O such that this holds, and you continue. Or you can say, let's take an alpha, assume that there is a U with that property.
Yeah.
And it's very easy to solve these equations. So there are... So there's always an existence, a uniqueness result, but I didn't mention that, which is, once again, there's an existence result. For any alpha, there is a U. That's true. And you can make it unique if you specify the reduction mod P of U. The reduction mod P of U. Yeah. So it's like a Cauchy problem. And it's a triviality, actually.
And is it...
It's a Hensel lemma thing.
Is it always, can it always be embedded in the subring of R?
So if you start with an alpha in GLN of R, there is, and if you fix a value mod P of U, there's always a U with this property.
Where? In R?
In R, yeah. And it's easy. It's a Hensel thing. So mod P everything is clear because R has an algebraically closed field, algebraically closed residue field. So modulo P things are true, and then you lift it by Hensel. Yeah. There's even for one by one matrices, there is even a formula, a fine closed form formula of U in terms of alpha, which I forgot, but one can write it down. Yeah. But for arbitrary n, there is no closed form formula, but you can do a Hensel type argument. So that is, and there are many other properties, like for instance, if alpha lives in the Lie algebra that I just defined of some subgroup, you will live in that subgroup, etc. It's what you expect. Yeah.
And does any of this make sense for more general schemes over R? Okay.
More schemes over R, more groups over R, maybe, or.
I meant something maybe like so we're thinking of R as functions, I suppose.
Yeah.
And you know, so you have something
you mean
bigger.
Other rings than R, bigger rings.
Mm-hmm.
I wrote everything for R,
Okay.
so I'm not sure. Yeah, I cannot answer questions that are outside R. I just made instead of R, you can take Vit rings over some more complicated field. So anything that's of the form of Vit vectors over an algebraically closed field of characteristic P, that's still okay. So this is the natural place for the whole thing. But of course, then you will have more constants. If the algebraically closed field is bigger, you add constants. So you actually don't want that, because you want no new constants or something. Whatever, yeah. Cool. Okay, so that's one theorem. It says generically the Galois group is inside what you were thinking that the Galois group should be. And this is the lemma. The lemma is fun, I swear. Yeah. For one thing, as I said, it cannot be settled at the infinitesimal level.
Yeah.
So that's an interesting thing. But maybe it's easier than I thought. I don't know. So my student came up with a number of wrong proofs that are shorter than mine. I think.
Tongue in cheek.
Yeah, I should. Yeah. So he said, but can't you do that? No. Can't you do that? No. But maybe there is a shorter thing that we both didn't see. Okay, so that's one thing. Let me state two more theorems, just to show you the flavor of these Galois groups. So once again, I have to tell you from the start that I have no Galois correspondence or anything. Although I strongly feel that there is, one can come up with some things. This group is of course infinite, because it has all the diagonal matrices with roots of unity and the Veil group. Since it has the Weil group, it has the Weil group, it has a permutation group inside, so there are a lot of finite groups in it, and they will feel they will be part of a correspondence somehow. So there are many interesting finite groups embedded into the symmetric group. For instance, all of them.
Yeah.
So who knows? Yeah, I haven't looked. I don't know. The second theorem, there's a gap. That's the problem. There's a gap between this, and of course the genuine GLM.
Yeah.
Because this is so close to commutative, and GLN is so far. And philosophically, I do not understand this gap. So, anyway. So there's a lot of things to think about here. What exactly... You cannot expect... What I'm trying to say is that you cannot expect a naive Galois correspondence because of this gap. So there's something else going on. Okay, the second theorem, you will see another genericity. It's a funny thing that you have these three genericities which are so different. So I want to take all to be ZP now, like this. So this is just a localization of Z at P. So it's a very arithmetic thing. The claim is that there exists a thin set in the sense of Diophantine geometry. I can recall what this means.
Thin.
Thin set inside Q to the n squared, so the n by n matrices with Q coefficients, such that for any alpha in with the Z coefficients, but outside the thin set.
I have a question.
Yeah. Ray Hubler, how about rings such as...
Oh.
Yeah.
What is DR?
Biederam is one of these Fontaine rings. Yeah, one of these Fontaine rings. I never looked at. Yeah, that's a very good question. Very good question. So these are. Yeah, I never looked at the interaction between the rings of periods of Fontaine. Can he hear me or?
Yes.
Oh, he can. Okay, so yeah. So these are very. So these are the rings where the periods live. In the p-adic theory of Fontaine, of course. Now I look at this much smaller ring, and this ring that I'm looking at, this R, also contains periods, but there are other types of periods. So in I'm not the person who says that, but Manin in that paper where he looks at, for instance, my work and compares it with work by others, says this. So I have to understand what Manin says better, but he says that the periods, the Fontaine rings, looking at such periods and looking at arithmetic differential equations in R are two different ways, two different things. So he says that they are different ideologically in some sense. So that's all I can say. So I've never looked at this, at the Fontaine ring. Yeah, the Fontaine ring has is a lot more transcendental, contains a lot more transcendental things than the ring R. And I was trying to stay as algebraic as possible, or as close as possible to algebraic things. Like, for instance, p-adic completions or number fields. Whereas these are so far away, so they are like rings of analytic functions on annuli or stuff like this. Yeah. Yeah, so might have answered some of that question. Okay, so there is a thin set such that for any choice of alpha, there exists a solution U of that equation that I'm talking about, with the property that G, the Galois group, is a finite group containing the Weil group, is a finite group containing the Weil group, the permutations. So this says that actually generically the group is finite, but it's a different kind of genericity. And it's a different setting completely, because here O is algebraic. It's actually just rational fractions. Whereas here, when you take a generic U like this, the alpha will be very transcendental. So the more transcendental the alpha, the bigger the Galois group might be. In some sense it is, because look what this says. Actually, this also says that the group is small. This also says the group is small. Maybe I should not interpret things the way I just did. Yeah, this says that the group is small. Mm-hmm. And that also says that the group is small because of this, but big because of that.
Right.
So they're different.
That's GLN.
Yeah, they're different. Yeah. So this is GLN of F1. So they are very different statements. This says both big and small.
Big and small.
Yeah.
But
Okay.
over F1, maybe finite doesn't mean small anymore?
Yeah, I don't know. Guys, I'm just telling you what I know. I don't know anything beyond these things. I just try to...
On a journey.
Yeah. So what is a thin set?
Yeah.
It's the thing that you see in the Fontane approximation, or in or more basic, in a more basic way in the theory of the Hilbert irreducibility theorem. Mm-hmm. So the definition of thin set is something like this. So it can be covered by finitely many things of one of the following forms: either closed, Zariski closed sets which are not the whole thing, or images of maps. Let's use the same dimension here. Images of generically finite, you can say finite, doesn't matter, maps over Q, which do not have a section over Q. So let's put Q's of Q. So if you have a map between X and an affine variety, and that doesn't have a section, then this map is far from being surjective. You cannot expect to solve the equations with right-hand side rational number here. And the image tends to be very small. It's called thin. And there is an estimate how many points there are in any ball in the image of a map like this, and there are far less than the number of points in a ball in the affine space, where by ball I mean you take z coordinates, not q coordinates. So that's thin set. So needless to say, this is a statement in the spirit of the Hilbert irreducibility theorem. So that's where you encounter thin sets, and the proof is via Hilbert irreducibility. So that's a Hilbert irreducibility, a trivial Hilbert irreducibility result. Well, trivial, yep, sort of trivial, yeah. So that's. But it's interesting that you have this finiteness, and that's based on a trick, and the trick I lifted from, with acknowledgement, from a paper on dynamical systems on PN. So there's a trick that people use when they study dynamical systems on PN. And this has something to do with dynamical systems on PN, because one views the map that sends x to the p as a dynamical system on Pn squared minus 1. So this is a map, an endomorphism of this. And once you realize this is an endomorphism of this projective space, once you realize that, you can start applying tricks that people use in when they study endomorphisms of PN. And there's a trick like that, and I lifted that trick, applied it here, and that's what gives the finiteness. So it's a sort of a well-known trick from this kind of literature. Okay, what's the third theorem? This is, so you see genericity in the sense of thin sets. And there is a theorem that sounds like this. There exists a subset omega of the first bare category. It's good. So, first bare category means it's a countable union of sets whose closure has empty interior. Okay, first bare category. I used to apply first bare category arguments quite a bit when I was younger, so that's good, it's cool. And it's always, you apply them like this, a countable union of proper subvarieties is never the whole variety. That's the typical way algebraic geometers use first bare category. So, anyway. So, yeah. Of the following metric space, we take U in GLN R with a property that U is congruent to 1 mod P. This is really like a polydisk in a numerical space over R. R is a metric space, so this is a metric space, a polydisk. Yeah. Such that for any u in x minus omega, if alpha is what you expect it to be, then there exists a subring in R such that alpha is there. Has coefficients in it, and the Galois group is exactly let me see something here. Yeah. Look, guys, this is not completely true.
Oh.
I'm sorry about this. This equality is not completely true. I said it, but I didn't write it, and now I'm going to make the correction. This contains a group called N delta, and this is GLN of F1. And I'm going to say in a second what is N delta. I'm going to define it there if you want, or somewhere. Here, I can say it here. N delta is all the guys in N whose entries are 0 roots of unity. Yeah, so N, delta N is 0, it's the same thing. So once again, N was the group generated by the torus with entries not necessarily roots of unity and the Weil group. And N is actually generated by the toral elements with entries the roots of unity and the Weil group. So this is like the constant inside N. And this is the claim that people make, that this and delta should be viewed as GLN of F1 bar. That's what I actually said when I said it. The group generated by the Weil group and the diagonal elements, diagonal matrices with entries, roots of unity, is this guy. You cannot, N is the full thing.
Yeah.
Yeah. N is the group generated by all the diagonal matrices and the Weil group.
Okay.
Okay. So, and this is an equality here. So this is a GLN, if you want, of F1 bar. So this says that in the sense of a bare category, a generic equation has this group as Galois group. So there's a tension between all these, as you see. This makes the Galois group finite, but that's because of how small O is, essentially, and the fact that alpha has Z coefficients. So it's an arithmetic thing. So these equations are much more arithmetic, and alpha is definitely not transcendental here. Alpha has Z coefficients. It's very far from transcendental. But here, alpha is transcendental, and there, alpha is quite transcendental a priori. Yeah. But you see, everything revolves around the same idea, namely that the Galois groups generically tend to be sort of related to either GLN of F1 bar or GLN of F1. So generically, the Galois groups are like GLN with constant coefficients. Okay, so how does one prove this? This is not hard again. None of these is hard, but they have their own little tricks. And the trick that I like the most is related to Theorem 1 because it relies on this lemma, which is a sort of unusual thing to do. People don't usually do this in Lie group theory. This is a Lie group.
That's a Lie group.
Yeah. Lie group theoretic thing. So this holds with P any number, doesn't have to be prime. Of course, because it better have nothing to do with prime numbers, because it looks very Lie theoretic. P can be any integer bigger than 2, bigger than 1, greater than or equal to. Okay, so these are the Galois groups. What is missing is a Galois correspondence, of course. And another thing that's missing is an analysis of Galois groups for other lifts of Frobenius, for other flows, for the flows related to SO, ST. These flows are not given by polynomials. They are given by p-adic power series. So you're suddenly outside algebraic geometry and formal geometry. And the Galois groups become, there's an extra twist to the Galois story, which is that results like this cannot be proved because you're too non-algebraic to even breathe. And even the definition of the Galois group, I have a more general definition of Galois groups, of which the one that I showed is a special case. And in that general definition, the Galois group is a Galois set, as I said, with some extra algebraic properties. So it's still a mysterious thing. So the only thing that's not mysterious is the case of these equations, delta u equals alpha u to the p. Okay, so that's the story for the Galois story.
How does n delta sit as a subgroup of n? What's the structure?
A subgroup of who?
N.
Of n. Yeah.
Yeah.
Subgroup.
Oh, so, but they're not diagonal. No.
No,
that would reduce.
N has this contains W.
Yeah.
Yeah.
Okay. Oh, it contains W.
Yeah, contains
That's
W
right.
and
That's
the torus of the torus of matrices with eigenvalues which are unity. Yeah, so they're not diagonal. They contain
What do the
W.
fixed fields of the subgroups tend to look like? Do you have any
Yeah,
examples?
that's a good. Yeah, so that's where
Sort of.
yeah. So you don't get the original ring all. You do not.
Oh, okay.
Definitely, you get much larger things, but I'm sure you can control that by classical invariant theory. It's just that I don't know what things you get, but whatever you get is interesting because I made some computations, and there's some interesting invariant theory. Think about this case here. You see, GU of O is finite. That sort of this case relates to usual Galois theory with finite groups. Everything is finite. O of U is U is forced to be have algebraic components. So actually, this boils down to usual Galois theory that we teach to undergraduates.
Polynomial Galois?
Yeah, polynomial. Yeah. So it's just
Finite.
this case boils down to special cases of usual Galois theory. It's just that I have not computed much. So, but it's as rich as usual Galois theory. That's what I'm saying.
It includes the usual Galois theory?
I don't know if it includes it, but it includes a lot of it.
A lot.
So because it includes Sn, which
Yeah.
includes everything. So
Yeah.
in some sense, yes.
Contains W.
Yeah, in some sense, you can say that. So there's a, yeah, and the invariants here are really usual Galois theory, but in a sort of crazy context. Here you have more invariants, and I made some computations, and one gets interesting functional theoretic invariants, not classical,
Oh.
because there are infinite groups. Yeah.
How exactly does the Galois correspondence fail?
The easiest way to see that it fails is that the invariants of this in O of U may not be O. They're bigger. So they're bigger. But they're bigger in a universal way. That bigger thing, once you only look at things bigger than itself, the Galois correspondence should hold, I guess. You understand what I mean? Yeah.
I mean, so again, if you allow to, if you do a factorial approach, if you allow extensions,
Yeah.
it still fails?
I have a feeling that it should fail, but let me tell you what I think should hold. So you have O, and you have O of U. You could take here O of U, the invariance. This is probably always not right, but you can look at intermediate things here, and they should correspond to subgroups of G. This is what I expect happens.
But on the other hand, if you allow extensions of constants.
Extensions of constants. Yeah, I never thought about this. Yeah.
So in particular, if you say that instead of considering G as a you allow to have points from arbitrary function.
Yeah, I never thought about this actually. Yeah, I was really always a prisoner of R. Yeah, yeah. It is not entirely clear to me how this theory works when you leave R and what exactly the right rings are for this theory, I swear. You know, because in differential algebra, we kind of have a feeling as to what the right rings are. What the category is, what...
Yeah.
Yeah, but here it's not entirely clear. It was never clear to me. Questions of rationality are never clear to me, and Galois theory is always about rationality. So this is just a one-step thing in the dark somehow.
So this could end up being a different way of rephrasing the same questions you just answered, but I'm wondering if there is something like a Tanakian formalism governing this Galois theory, and I say like because it's so nonlinear that you would expect that.
Yeah,
but, and you know, and then also maybe is there a version? Can you talk about a delta of algebra with this delta, but in a similar way as the differential Tanakian theory? And
my general feeling is that, well, the answer is I couldn't find any Tanakian framework for this, or any Hopf framework for this. Another thing that I couldn't, that's all. Another thing that I could say is that actually I gave a talk where Manin was in the audience, and he asked me exactly the question you asked. So that's another. And third, he made Manin made a suggestion, an interesting suggestion about trying to implement a certain Witt construction in a non-commutative case. Now, the author is who looked at these non-commutative Witt rings is a Russian author, but I forgot his name. But I have if you Google non-commutative Witt, there's only one person. That's the person who wrote quite a few very interesting papers on the subject. And they're already published, and I think he's at Seclo, actually. So it's like a known person, but I didn't know about him before Manin mentioned him. So it's maybe not one of the regular suspects.
If you look at, to get back to what O square brackets U looks like, that's finitely generated. But what about its subrings? Did you say there were new constants between O and R? Between O and O of U, you didn't?
I didn't say that, but what I did say is that the constants, these two rings, tend to have, the constants are not that different.
Oh, that's what you said.
Yeah. This guy may have some more constants, but not really like substantially new constants. All the constants of this guy are actually algebraic numbers, they're roots of unity. So the point is, this guy, all its constants are roots of unity.
So that doesn't disturb anything? That there's no consequence?
It didn't disturb me.
You don't have to get rid of them?
No, No.
I was thinking in the Colchin, with Colchin's approach to P-Carvesio theory, he specializes down to get rid of the constants.
Yeah, so, but here the new, let's say that they're algebraic, so you cannot specialize.
You can't do that.
Yeah.
I see.
Yeah. So all the constants here are algebraic, so there's no specialization. And on the other hand, I didn't feel like I need to get rid of them, but maybe